Hello, welcome back to Algebra. The title of this lesson is Graphing Points in 3 Dimensions and also Introduction to Functions in 3 Dimensions. So right at the beginning of the lesson, when I get really excited about teaching you something, I usually try to tell you, and this is one of those lessons. Some lessons I kind of just get through it because it has to be done, and sometimes I'm really excited about it, and this is one of those times. Because this concept of graphing points and functions in 3 dimensions, it seems very complicated and difficult to understand. When you flip through most books, you see a lot of complicated diagrams, and most students really just keep flipping the page and they don't quite understand exactly what the book is trying to tell them because the book has everything thrown at you all at once, and the graphs look very complicated. So here we're going to take it from the very basics. We're going to talk about graphing in 1 dimension, graphing in 2 dimensions, which we've been doing all along, and then the concept of graphing in 3 dimensions, and I'm going to illustrate along the way how you can have a function that exists in 3 dimensions. And not only how you can have it, but actually kind of a practical understanding of an example of why you might care about that. Because in real life, when you get past all this stuff and you get past calculus and physics and in the real world, everything is in 3 dimensions. The pipes that are flowing the water or the oil or the gasoline or whatever we're piping, it's a 3-dimensional thing. It has length and width and height, right? Everything, the weather systems, the climate, energy production, all of that stuff is really happening in 3 dimensions. So we have to take our math from the basic idea of a 2-dimensional XY plane, and we have to translate it into something that exists in the real world, which is 3 dimensions. And actually, when you get even in more advanced physics, we introduce the concept of time, which is the 4th dimension, and we merge space and time into something called space-time, which is actually a 4-dimensional thing. And that's way beyond the scope of this, but just know that the things that you're learning here are very much important for very modern understandings of physics and engineering and science. So just the things that we're learning here is very important. So we have to start at the beginning. Remember, the very first thing we learned how to graph was something in what we call 1 dimension. We call that the number line, right? So when we talked about the concept of graphing something in 1 dimension, call it 1D for 1 dimension, right? That means when we have 1 dimension, that just means there's 1 number involved, right? 1 number involved. So I'm going to say that, just write this down here. We have 1 number, right? That means we have something we want to represent as a single number. So we might represent it as, for instance, x is equal to 2. It's just a single number. How do we, there is no y here. There's no y because there's no xy plane. We don't even have that yet. We only have a single direction and a single number, x is equal to 2. How do we graph that? We use something we call the number line, right? And we used a line because a line is what we call a 1-dimensional object or a 1-dimensional surface, because you can only go back and forth in this single direction, either this way or this way. There's no y direction to it. There's only an x direction to it, like this. Now to graph this, you all know here's 0, here's 1, here's 2, here's 3, here's 2, and here's 1. In order to graph this, what we did is we just put a single dot on x is equal to 2 like this. And so single number, single dimension, single dot. Now, of course, we had other numbers than positive numbers we could graph here. We had, for instance, if we wanted to graph x is equal to -3, we could, of course, graph that on a number line as well. And the way we do that is we say, well, these are the positive numbers. And going the other direction, we have negative numbers. So here's -2, here's -3, like this. And so to graph the single number -3, we just go to the left and we put a dot on -3, and a single dot is where we are. But notice that in every one of these cases, we had to use a 1-dimensional graph, which is just a line. It can only go in 1 direction, back and forth, to graph a single number. Right? That's what we did. Now, an example, a practical example of when you would ever care about this, well, you might care about it, for instance, let's say you're talking about how much money you have in the bank right now at this moment. So right now I have, let's say, $10 in the bank, or 10 pounds, or 10 francs, or wherever you live in the world. I have 10 units of money, okay? That's a single number, and it represents how much money I have right now. So I could graph that on a number line if I wanted to. Now, 2 days from now, maybe I have $15 in the bank. That's a single number. At that moment in time, 2 days from now, it's a single number. I could graph that on a number line. So a practical example of a single number graph like this would be how many dollars you have in the bank. It's just 1 number at any given time, okay? Now, we have more complicated situations. So we have 1 dimension, 1 number requires a graph that has 1 dimensions. All right, so now let's say we're graphing something in 2 dimensions. 2D means 2 dimensions. And that means that we need to graph 2 numbers And we called those numbers x and y because we had to give them labels, right? So we called this the xy plane. This thing we just called the number line, but now we have to have essentially a number line going this way in the x direction for the x numbers, and then we had another number line which went up and down called the y direction. So we kind of had to have two number lines, one for the x direction, one for the y direction, and together they no longer form a single line, they form a plane. So a one-dimensional graph is called a number line, and a two-dimensional graph that we use to graph these two numbers at a time, that thing is called a plane, an xy plane. And we have been doing this, forever. So we can, of course, draw our friendly xy plane. We've done this so many times, I don't need to spend, a lot of time on this. You all know what an xy plane is by now. But let's say we want to graph a couple numbers on this xy plane. Let's say we have number 1, number 2, number 3, number 4. Here's 4, here's 3, here's 1, 2, 3, 4 right here. Let's say we want to graph some numbers on here. So let's say 1, 2, 3, 1, 2 is right here. What does this point really represent? It means that this point represents 3 units in the x direction and 2 units up in the y direction. So we said that this point was 3, 2, and it was always read x, y. But notice that every one of these dots here that we can plot required 2 numbers to represent it. So this thing really required 2 numbers. And because it required 2 numbers, we had to have a graph in what we call 2 dimensions. We call it an xy plane. And this 2-dimensional surface is an extension, a more general extension than the single number line we have. And of course, we can draw different points in different places over here. We can go in the negative direction too, -1, -2, -3 like this. And we can go, here's -1, here's here's 3 right here. So we could put a point, for instance, here at -2, 3 right here. And so this point is -2, 3, because we go -2 units from the left and then 3 units up like this. But no matter what dot we put on this plane, it requires 2 numbers to represent it. Every dot in the original graphs for 1 dimension only required 1 number. So you see, as we have data, or as we have information we're trying to represent with a pair of numbers like this, we require a more complicated graph. Now, what would be a practical example of really needing to draw a graph in an xy plane? Well, here's a practical example for you. Let's say we have a bar. What I mean by a bar is a metal bar, a metal rod, right? Let's say it's about this long, okay? Now this bar it's made of metal, and so it has temperature. You can measure the temperature at every point along that bar. If it's just here in the room like this, then of course the temperature here will probably be the same as the temperature here, and the temperature here, and the temperature everywhere in the bar should be about the same, right? But what if I have this bar, and I take a blowtorch, a flame, and I put it right in the middle, underneath the middle of the bar? Then the middle of the bar will be hot, but the edges of the bar will be cooler. And so the temperature along the bar in that case is going to be different, and so we might want to measure that. In fact, that's the kind of thing we do all the time in spacecraft. We might want to know the temperature of the wings. The leading edge of the wings is going to be hotter than the trailing edge of the wings. The temperature of the landing gear when it hits the ground is going to be hotter than the other part of the ship that's not touching the ground. So there's temperature gradients all over the place. So it's just one example. So how would we measure something like this, right? If we wanted to do an XY plot like that, then what we would have is, let's go ahead and draw a quick little XY plane here. I'm not going to do anything too fancy. So here's X, here's Y, like this. And we're saying that we're going to draw some kind of bar. So let's say that underneath the X axis, let's hang this bar off. I'll try to make it equidistant on both sides, as best I can do, let's say. And this is a bar here, right? Now let's say that right here, I put like a really big flame, like a blowtorch or something, like this, underneath this part of the bar. And then over here, I also put a flame, but maybe it's not so big. Something like this. And here, there's no flame anywhere else. It's just a giant torch right here and a smaller torch right here. Then what would Y be? Instead of calling it X and Y, we could call it the temperature in degrees Celsius. And in X direction, we could call it, that's the distance in meters along the bar, where the center of the bar is at 0 meters. All right? So then we can say, for instance, that we have 1 meter, 2 meter, 3 meters, 4 meters, 5. You can just do tick marks here. So this is 1, 2, 3, 4. Here's 5. Here's 1. And then we have -1, -2, -3, -4, -5, -6, -7, so something like this. So here's -1, 2, 3, 4, -5, and you can go like this, all right? And then what do we do for the y-axis? Well, who knows what the temperature is going to be, but let's just say, we have 5, here's 10, here's 15, here's 20, here's 25 degrees Celsius. So 5, 10, 15, 20 for that. Okay, so what do you think this is going to look like? I know that you all have a pretty good idea of what it's going to look like. Well, what's going to happen is over here, far away from this, probably the temperature is going to be pretty low. Probably pretty low. In fact, every little point that we measure is probably going to be pretty low, right? But then when we start getting close, maybe the temperature goes up just a little bit, right? And then when we get right under the flame, maybe the temperature is like way up here at 25. And maybe it's like that for 2 tick marks. But then maybe when we get on the other side of it, it's maybe like down here, and then maybe it drops down here, and then maybe it drops, I'm getting in the way of my stuff here, but right there. And then we get underneath another flame here. Let's say that my flame, let's move this dot here. And then maybe it's back up here, maybe here, and then it goes maybe down here. And then we get far away from that flame, and then we have something like this. You see, I have a bunch of dots here, right? Now I can label the XY point of every one of these dots, but I'm not going to because it's going to take forever, but we can label some of them. Let's say, what would this dot be? Well, it's -1, 2, 3, 4, -5, comma, 10. So this would be -5, comma, 10 right here. How would we represent this point right here? These 2 points, really. Well, let's look at this one. -1, -2, -3. Here's -4. -4, comma, 25. -4, comma, 25. Where the second number is the temperature and the first number is the distance. Negative distance just means it's on the other side of 0. It's not something crazy or mystical. In fact, if you go on the other side here, let's take a look at, like, let's say this one right here. This is at 1, 2, 3, comma, 15. 3, comma, 15. So you see every point here, every green dot really requires 2 numbers to represent what's going on. One number for the distance along the bar, and the other number represents the temperature. Every single green dot requires 2 numbers, and because of that, it needs a 2-dimensional graph like this. And if you want to be cute about it, we don't have to, but if you want to be cute about it, you can connect these dots. You can kind of either make straight lines or you can make smoothed out kind of things. But let's go ahead and connect them just to show what we have here. So we can go down like this. I didn't even put a dot in the middle. Let's just say it's right there. And we go up here, we go here, down like this. Now, what does this look like to you? I mean, of course, it's a bunch of dots with a bunch of lines, but what does it look like to you? It's a function, right? We've talked about functions. We've talked about functions of x. So if x is the direction along the bar and t is the temperature, then the temperature of this bar is a function of x. It means it depends on x. The temperature depends on x. Why? Because these flames are at different locations along x, right? So when we have a 2-dimensional graph like this, every point requires 2 numbers, and the dots that you get when you connect them all together, we can say form a function. So we say that the temperature is a function of x. And the way you write that in mathematical terms is you say the temperature is basically, you can put a little arrow or however you want to say. You say it's a function of x, right? Or you could even write it as t as a function of x here. You could just say t of x. T depends on x. Now, the exact equation that describes this line, this is a bunch of dots here. I can't come up with a function that's going to fit all those lines. But when you get into higher classes in math and in statistics, you can take any set of points you want and you can find a function that goes through those points. You can do that for any number of dots, no matter how crazy they look. You can find a function that goes through them all. And so then you would say that you would be fitting the data with a function that goes through your points. All right, so now we're getting to the punchline. We have a single number. This could be the amount of dollars in your bank account. Single number requires a single dimension number line, and we put a dot there. 2 dimensions require, or points that have 2 numbers require a 2-dimensional XY plane. And an example of that would be when just a single example would be when the distance along a bar has different temperatures. And so you would say the temperature is a function of the single variable x. That's what we've been saying all along, f of x, f of x. So now we need to talk about what happens in the real world when we have points that do not have 1 number or 2 numbers, but what if the point you have requires 3 numbers to plot it? How do you do it? So it's not going to be a one-dimensional line or a two-dimensional plane. It's going to be a three-dimensional space. So in general, instead of just x and y being in a plane, then in real life you have x going towards you and y going this way. And so that forms the xy plane down here in the plane of my paper right here. But then the z direction is a new variable that comes out of the plane. So you have x going toward you, y going this way, that's the xy plane we've always had, and z comes right out of the page. So you have three different directions to plot three different numbers for every single point. All right? So what we want to do now is we want to get some practice with drawing this and plotting some simple points. And then we're going to talk about what a function in 3 dimensions might look like. All right, so let's say we have a point and we want to plot the point 0, 3, 4. So this means the x coordinate is 0, the y coordinate is 3, and the z coordinate is 4. You always read it x, y, z, just like xy points you read xy. It's just x, y, and you have a new coordinate called z. So here's how I want you to draw these things. They're very difficult to draw on a paper, but this is the best way I know of. And you might have a different way, but this is the way I do it. And so you can hopefully take my advice or follow, do it your own way. That's fine, as long as you get the right answer. What I want you to do is draw a line up like this, okay? And then I want you to draw a line going kind of at an angle like this. And then I want you to draw a line like this. So you see how this kind of forms a corner? You can think of this as the corner of a room, right? So this direction is the x direction. That's coming out of the board. The y direction is this way, and the z direction is up. Now, I need to make sure you understand here. This is a drawing on a board of a three-dimensional thing, so the perspective isn't quite right. What's really happening is the x direction is going toward you. This line is supposed to be coming straight out of the board, but I can't draw it out of the board like this. So you got to kind of do it at an angle like this. So it's x, y is going this way, and z is going straight up. Now, the way that you know to get the direction of the x and the y and the z is when you take your right hand. If you curl from the x into the y, your thumb should point z. So it should always be x, y, z, because if you curl, it should be x curling into y, giving you z. If you accidentally flip x and y, it's not going to work out that way. It has to be done this way in order for you to have the right x, y, z system. All right, now if we want to plot x is equal to 0, well, first, actually, before I do that, let me draw some tick marks. Here's 1, 2, 3, 4. 1, 2, 3, 4. And 1, 2, 3, 4, like this. So how do we plot the point 0, 3, 4? All right, what we're saying is the x coordinate here, this one, the one that comes out of the board, is 0. So it doesn't come out of the board at all. Right, but the y coordinate is 3, so we go over to 3, and the z coordinate is 4 up here. So the way you do that is you put a dot right here, but see, it's very difficult to know what that dot means because it doesn't really tie, you can't really see the x coordinate so easily. So what you need to do is draw a little dotted line like this, and a little dotted line like this. And this point is 0, 3, 4. The dotted lines are telling you that this point lies in the plane of the board right here. The x coordinate, the x direction comes out of the board, and since the point is in the board, there's no x value. X is equal to 0. So the dotted lines are showing you the point is in the plane of the board, 0 for x, 3 for y, 4 for z. And that's how you plot that point. Okay? Now we're going to get a little practice doing a few more of these. And they get kind of fun after a while. It's kind of interesting. It's doing something a little bit different. So let's plot the point 2, 4, 0. So x is 2, y is 4, and z is equal to 0. How do we do that? So the first thing you do is you want to draw your XYZ system. You go down and you go to the right, just like an XY plane, and then you put your pencil back here and draw an angled line like this so it looks like you're looking at a corner, and you always label it the same way, x, y, and z. You should always be able to take your right hand, cut through x, into y, and your thumb should point to z. That's the correct labeling of the axis there, of the axes there. All right, so we can draw some lines. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4, like this. Now, x is equal to 2, so we have to go down to 2 right here. Y is equal to 4. 1, 2, 3, 4, right here. but there is no z value. That means that the point there does not go up at all. So the way you draw that in perspective is you go to 2, which is right here for x, and then you go to 4 here, and you have to kind of draw it as a perspective, something like this, right? This point is 2, 4, 0. How do you know? Because it's saying you go 2 distance units along x, 4 distance units along y, but because the dotted lines are basically telling you that the point is in the plane of the xy plane, basically there is z value is 0, so it doesn't go above the plane there, because the z-axis, remember, if this is the xy plane, the z-axis comes up and out of it, and since z is 0, then the point is in the plane there, in the xy plane. This xy plane is on the bottom, the z-axis comes out, and so this point is in that plane. That's what the dotted lines are trying to tell you. All right, let's do a couple more. Let's let me try to fit 2 of these guys here, so that we can. I have something important I need the entire board for on the next board here. Let's plot the point 2, 0, 1. This is x, of course, y, of course, whoops, z, of course, for this guy. Right, like this. And so what we have is to draw our axis, you go straight down, straight across, put little arrows, then go back to the origin and draw a slanted line out this way. This is always labeled x, this is always labeled y, this is always labeled z. All right, so then how do we plot 2, 0, 1? So let's draw some tick marks. Here's 1, 2, 3, 4. Here's 1, 2, 3, 4. Here's 1, 2, 3, 4. How do we draw this guy? X is 2 units. But y is no unit. So I don't actually go this way or this way for y. I'm kind of stuck on the axis here. But then z, I go up 1 unit. So it's kind of like this. You go 2 units in x, and then you go, let me just double check myself. Then you basically go 1 unit in z, and you got to go down and draw, whoops, I went a little too far. And then connect this dotted line down here. Your point is basically right here, and the point here is 2, 0, 1. 2, 0, 1. Okay, because the x coordinate is 2 units, the y coordinate is no units. You didn't go anywhere in y, but you did go 1 unit up in z, and these little dotted lines are trying to draw something on a board to give you the perspective, but the perspective never looks quite right. Okay, it's never perfect. But you can kind of see that this is in the plane of x and z right here, because there is no y value. All right, we're going to do one more of these before we kind of conclude the section. What if we plot the point 3, 4, 5, 3, 4, 5. So notice, so far, I've chosen these points carefully. One of the coordinates had a 0 value, so this was in the plane of the the y, z plane like this. All right, and then this coordinate was 0, so then this one lied in this plane. This coordinate was 0, so this one lied in this plane. So far, I've had one of the coordinates always set to 0. This is the first point where all of the coordinates have a value to it. So let's go ahead and set up our coordinate system. So we have to go down, we have to go over. This is going to be, whoops, this is going to be diagonal like this. So we have x, we have y, and then we have z. And we have to at least have 5 units here. So let's go 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So here's 5, here's 5, and here's 5. So how do we draw this? We know that x is equal to 3, so we have 1, 2, 3, so here's 3 right here. We know that y is equal to 4, so from this point we have to march over 1, 2, 3, 4. But then we have to somehow go up with 5 units, so it's very difficult. So what you do is you go 3 units this way, and then you got to go to 4 units this way. So you draw your little diagonal line down like this, parallel with this guy. Then you go over here like this, so they join here. So this is 3, 4, this is 4, 3, 4, and then from this point you go all the way up to your final location of 5. 3, 4, 5. I want you to burn this in your mind. This is probably the best way you can draw a 3-dimensional point on a 2-dimensional piece of paper or a 2-dimensional board. You have to draw it some kind of way, and it's very difficult to do it because you have 3 dimensions but a 2-dimensional board. So the best thing you do is you draw your x-axis obliquely at an angle like this. You go, in this case, 1, 2, 3 units in x, 4 units in y, but you kind of have to do the angle dash thing to get the perspective right. And then from this point, from this point, you go up to 5 units, but again, the perspective isn't quite right because you see, you can look at the distance, it doesn't quite look right. 1, 2, 3, 4, 5 units. What you're really saying is that the XY plane is a flat thing. So you go, in this case, 3 units of X, that's toward you, and then 4 units in Y, that's this direction. So you're in this location in the plane. Then you go 5 units, 1, 2, 3, 4, 5 up. That's what you're really doing. 3, 4, 5. Remember that. 3 toward you, 4 in the Y direction, 5 up. But you can't draw that easily, so this is kind of the best way to draw it. Now you can of course draw these kind of diagrams for negative values, -3 or whatever. It's just gonna, you gotta go this way and down, and it gets very confusing to draw it, so I'm not gonna do any more problems, but you can of course do these kinds of things. Now the real example, the real question is, what kind of practical example would you ever have for plotting 3 numbers like this? Well, remember our example back to the bar. We had a bar that was just a straight line bar, and we plotted the temperature at different points along the bar. What if instead of a bar, we had a plate? Let's say we had a steel rectangular plate. This piece of paper is now a steel rectangular plate. And every point on this XY plane down here, it has some temperature involved. So the location in the plate is going to be given by X comma Y. But at that point is a temperature T. The temperature might be 10 degrees Celsius. The temperature might be 50 degrees Celsius. The temperature might be 0 degrees Celsius. But every point in this plate is going to have a different temperature. How would you graph or represent something like that? Well, let's just say that we had this plate, and just to make it interesting, just like in the previous example, let's say I had a blowtorch, a very hot flame. I put it right underneath the center of this plate. The center of the plate is going to get really, really hot, maybe 1,000 degrees or 100 degrees or something. But all of the edges here is going to be much, much less. So we're going to draw kind of a little representation of what that might look like. Okay, so let's say we have this plate, and we have a flame underneath there. So before we draw any kind of plate, we have to draw our XYZ system. So here's one direction, here's the other direction, and here's the other direction like this. So this is X direction. We're going to say it's in meters. That's how we're measuring the length along the plate. And then we have the Y direction. This is also in meters, so we can measure where we're at in the plate. But this direction, the Z direction, is not in meters. It's in degrees Celsius, because the height above the XY plane, how far above the XY plane the dot that we put is going to represent how hot it is there. The higher above the XY plane means it's hotter, and the lower down near the edges means it's going to be colder. So you're kind of using height above the XY plane to represent temperature, right? It's very common. This is the kind of stuff you do in engineering all the time. You measure temperatures, you plot temperatures, you have lots of beautiful software to make these beautiful plots. So where is our plate? Okay, we said we had a plate. It was in the XY plane. Well, our plate is in the XY plane here. So our plate really extends all the way, let's just say, from here to here like this. So this whole area, I'm not going to trace over the blue with the green, but this whole area here, in fact, I got my perspective wrong, so I'm going to erase that. Try to do it a little bit better. It should be shallower, more like probably something like this. Something like that, yeah. So my perspective was a little bit wrong, but you get the idea. Here's the plate, which is in the plane. This is the plate right here, okay? And underneath this plate, I'm going to draw right in the center kind of a flame. I'm going to put dotted line here because it's kind of hidden, but when it comes out, I'm going to color this guy in, all right? So here is a nice, flame. It's really hot, and it's centered right on the center of this plate. So the center of this plate is going to be really, really, really hot, and the edges here are going to be much, much colder. All right, so if I were to plot something like this, the location of this guy right here, the location of the tip of this flame is something like this. In the X direction, it's right there. And in the Y direction, you got to kind of go with the angled thing like this. So this is representing the X coordinate and the Y coordinate, right? So let's say up here, this is like 500 Celsius or something like this. Then if you go all the way up from the tip of this flame, that might be 500 Celsius. So depending on the length and width of the thing, I could say that this point is something like, I don't know, 4 units in the X direction, 4 units in the Y direction, because it was kind of in the center. And then the last point was 500 Celsius, because it's way, way high right there, okay? And then what would a point way out here in the edge look like? What would a point, let's say a point right there. Well, what you would do is you would kind of put your little dotted line. It would be something like this, and then this dotted line would be something like this, and then the height of this thing would be represented by whatever. So let's say this is like 10 degrees Celsius. So then you would go up from there, something like this. So you see the distance above the XY plane is much, much lower. And the coordinates of this point, I'm just making up numbers here, but this might be, if this were 4 meters, this might be like, you know, I don't have it quite right, okay, but this might be, you know, 7 meters, and then 7 meters in the other direction. And then it might be, you know, 10. So 7, 7, and then 10 up above. So that's not quite right because the center of the thing was at 4, 4. So I don't have it quite drawn, so everything should be centered. But the point is, the farther away you get from the center, the smaller and smaller this temperature number is, and you represent that by a point that is physically closer to the XY plane. So that's what you see a lot of times when you look at like very advanced, you know, plotting, you know, look at something from NASA or look at something from an engineering company, they're going to plot the temperature gradient somewhere and you're going to see these beautiful plots with curves everywhere. The height of those things are representing something, usually temperature, pressure, or something like that. Sometimes they use colors as well, right? So if you can imagine of all of these points, you have a point right here. It's going to have some height above the plate. You're going to have a point right next to the flame. It's going to be almost as high as that one, but not quite. A point over here, just a little farther from the flame, it's going to be a little bit lower. So concentrated around the center of this plate up here is going to be a mountain. And then it's going to come off and it's going to get smaller and smaller in all directions as you go. So I can't draw that so easily, but if you can imagine, let me use a little prop here. If you can imagine, okay, that you have the XY plane right here, right? You have the XY plane, and then out of the board comes Z. So instead of looking at it at an angle like that, think of it as X and Y, and now I'm looking down. I'm looking down, the Z axis is coming straight out towards you, right? Then the thing might look something like this. The plate is essentially, you know, over here somewhere, and the center of the plate is that flame, and so then I might have some points really high above the above the plane here representing a high temperature, and then near the edge, they're going to be closer there like that. So I can't draw in 3 dimensions. I can't even draw in 2 dimensions, but I'll try. If I had something like this, you know, it might be X, might be Y, might be Z, and then I might have my, you know, big flame right under the thing right here, right, the plate. Then what's going to basically happen is you're going to have the highest points right here, and they're going to fall off like this. But the problem is this looks like a 2-dimensional thing, but really it's happening behind as well. You're getting fall off in both, you're getting fall off in the direction of the board and everything. It's basically a mountain that's very high going off this way and going off towards you and me. So it looks literally like a mountain above the XY plane, where the height above the XY plane is the temperature. Okay? So here's the punchline. Whereas before we said, in this case, the temperature was a function of only X because X was the thing it depended on. But you see here, the temperature is not only a function of X, it's also a function of Y. In other words, the temperature is a function of how far I am this way, but it also changes depending on how far I am this way. So we say that the temperature is a function of X and Y. So another way you write that is you say that the temperature of this thing is a function of X and Y, a function of 2 variables. Why is it a function of 2 variables? Because the temperature changes depending on how I move in X, and also changes as depending on how I move in Y. It is dependent on 2 different variables, one of them called X, one of them called Y, which is just the location in the XY plane there, right? So in 1 dimension, it's a function only of X because there's only 1 dimension of distance, but here it's a function of 2 different variables. Now, this opens your mind to more advanced science and math, right? Because in real life, there's an electric field in this room, and it's a function of lots of different variables, a function of the X, Y, and Z. And then you have pressure in a pipe is a function of X, Y, and Z, maybe. So you have functions that can be functions of more than 1 variable depending on the system that you have right here. And I'm just trying to give you motivation. We're not teaching that. We're not getting into details there. I'm giving you the motivation. Some people would say, why do I care to plot a point in 3 dimensions? Why do I care to plot this kind of thing in 3 dimensions? It's because the real world is 3 dimensions. If I have a surface I'm trying to design, I need to know what the stress is, what the pressures are, what the temperatures are all along that plane or whatever it is. And maybe it's an aircraft wing, or it's the blade of a helicopter, or it's something along a pipe or something like this. So oftentimes, in fact, all the time in real life, whatever you're trying to study is a function of more than one variable, just like this temperature is the function of more than one variable. So the point of this lesson was to teach you about three-dimensional plotting in 3 dimensions, points mostly. But we also introduced the concept of a function, which was a function of 2 variables, which creates kind of a surface in 3 dimensions like that, x, y, and z. Now, to blow your mind further, I mentioned it once before, but when you get into more advanced physics, you realize that time is another dimension. So you have x and you have y and you have z. Those are the dimensions of distance. But then you also have, at every point in your plot, a time dependence. Everything changes in time. So that creates something called space-time. Space and time are kind of linked together. That's much more advanced than what we're getting at here. And so you end up talking about space-time, and you try to plot things in space-time, and it gets very confusing very, very fast. But everything we're learning here is very much required to understand all the advanced things that you'll learn down the road. So make sure you understand these concepts, and then follow me on to the next lesson where we're going to finally use what we learned here to talk about solving systems of equations that exist in 3 dimensions.